I want to talk a little bit today about assigning quantum numbers to electrons. And quantum numbers are how we describe the position and orientation of electrons around an atom. And one thing to keep in mind before we start this discussion is when we specify an electron with a set of quantum numbers, we're not really talking about a location for that electron. One of the principles of quantum mechanics says that we cannot precisely specify the position of an electron. What we're really doing is we're talking about the probability of finding an electron in a certain region of space. There are generally 4 quantum numbers that we use for describing the electrons in an atom. The first number is called the principal quantum number, and this is the one that's usually associated with the electron's shell. It's given a value of 1 or 2 or 3 and so on. In this diagram, this is the nucleus in the middle, the 1 shell, the n equals 1, and n is the symbol for the principal quantum number, is the closest to the nucleus. N equals 2 is further away, n equals 3 is further away, and so on. In general, the further away an electron is from the nucleus, in other words, the higher its principal quantum number, the higher in energy it is. The second quantum number we use for describing an electron is the orbital quantum number, and this is generally used to describe the shape of an orbital in the shell. These principal quantum numbers, they're given the symbol L, are usually associated with a series of letters. So the number 0 equals S, 1 equals P, 2 equals D, and 3 equals F. So these are the orbitals that a lot of us are familiar with talking about, and they have shape. So the S orbital is a symmetrical orbital, and it's important to remember that there is a node in the center of the orbital. Right in the middle there's an area where there is no electron density. That corresponds to the nucleus. The p orbitals, there are actually 3 p orbitals, one along each of the axes, and they have a bilobal shape with a node again near the nucleus. I don't have the structures of the d or the f orbitals shown here because there are more of them, they take up more space, and they're more complicated. And I don't really have the opportunity to show them on this document. The magnetic quantum number, this should be m sub L, so this should be subscript. Let me just do that. M sub L. This indicates the direction of each orbital. So for instance, we said we have 3 p orbitals, one along each of the axes. So the m sub L, the magnetic quantum number, would indicate the direction of each of the 3 p orbitals. Since there are 5 d orbitals, there would be 5 magnetic quantum numbers corresponding to the d orbitals, and 1 for the s, since there's only one s orbital. The sort of rule for figuring out how many magnetic quantum numbers you're going to have is that you look at the number L, and there's going to be 2L plus 1 of the magnetic quantum numbers. So, and there's this, in this example, in the second shell where n equals 2, it contains 4 orbitals. For s equals 1, there is only one s orbital. For p equals 1, for L equals 1, which is the p, there are a total of 3 p orbitals. And finally, the last quantum number is the magnetic quantum number. Again, this should be m sub s. So let me fix that and make it a subscript. And each electron can have a spin of plus 1/2 or minus 1/2. That's what the spin quantum number describes, is the spin of the electron. And something we're going to talk about in more detail in another document is that no 2 electrons can have all 4 quantum numbers the same.